Hello, good evening. My name is Chris and I'm the founder and director of the Northern Ireland Science Festival. You're all really welcome to this year's digital edition of the programme. And this year we're really excited to be once again partnering up with the Open University. As many of you have known and hopefully watched over lockdown, the BBC series A Perfect Planet has inspired not just us but a whole generation of new science fans. And we're really delighted tonight to be presenting two of the scientists that have been behind that show. Special thanks once again must go to the Open University. And if you do like what you see tonight, please follow us on YouTube, hit that like button, hit subscribe and follow us for more content at nisciencefestival.com. Thank you.
Good evening, everyone, and on behalf of the Open University, welcome to our conversation about A Perfect Planet, which will look at the science of our recent prime time series in partnership with the BBC. I'm John Darcy, the director of the Open University here, and we are delighted once again to be working with the Northern Ireland Science Festival. This event will be a journey of words, pictures and video as we learn more about our extraordinary planet and gain insights into the science that helped create this landmark BBC programme. I am delighted to welcome two of the Open University's fantastic academics who worked very closely with the BBC to develop the content for the programme, Professor Stephen Lewis and Professor Hazel Rymer. If you would like to get involved on social media, you should connect with us on Twitter at OU Belfast, on Facebook at Open University NI, and of course at NI SciFest. So that's enough for me. Let's hear from Professor Stephen Lewis and Professor Hazel Rymer. Welcome to the Northern Ireland Science Festival.
Hello, my name is Hazel Rymer and I'm the Emeritus Professor of Environmental Volcanology at the Open University. And I'm going to talk about what I think makes for the perfect volcano. So what makes a perfect volcano? Well, they're all perfect in their own way, of course. This is Askja volcano in Iceland. Look at the serenity and beauty of this volcano. An ice cold lake there, about 8 kilometers across, 200 meters deep. And in the foreground, a little lake that is warm enough to swim in. Amazing, you've got everything at this particular volcano. Here's Etna. At the time I took this picture, it was having a little bit of a lava eruption going on, and you can see the beautiful city lights down below. Pretty stunning. Here's another volcano in Nicaragua. This is Masaya volcano, and you look down into the active crater there, and sometimes you see this stunning sight, a broiling, bubbling away lava lake. But as a volcanologist, what I need to do is to be able to make measurements on volcanoes. I need to be able to get there regularly whenever I need to. And I need to have a volcano that has changes that I can measure so that I can learn from the changes that we see over a relatively short period of time, weeks, months, years, and to learn from that to infer what's going on at perhaps larger volcanoes or volcanoes that don't erupt quite so frequently. So here's Stromboli volcano, very beautiful, relatively small volcano, and as you can see, quite active sometimes. Now, the problem with this volcano is that you have to usually arrive by boat and then cart all of your geophysical equipment to the top of the volcano on your back. And although it's a relatively small volcano, it's a very long way up there. So there isn't a very neat and easy to use road that goes all the way to the top. Contrast that with Iceland. This is the way to Askja volcano. In fact, this is almost inside the Askja volcano. You can see that although it's covered in lava flows, there's a very nice road that goes right up there. We can get our four-wheel drive vehicles very easily up there, and you can see us making measurements there in the foreground. Even when this area is covered in snow, as it is most of the year, you can still find the road through these lovely yellow sticks. So quite accessible. On Etna, of course, there are roads and you can walk and there are good paths. But there are some parts that it's much easier to get to by helicopter. And so we do this very, very occasionally, get a lift there. On this particular occasion, they didn't come and pick us up, partly because there was something else going on further down the hill, this lava flow going quite gently down to the town of Zaffarana, which is just on the flanks of Etna. Fortunately, none of the houses were destroyed, just this one here on the outskirts. And you can see that the people owning it weren't really very happy at the time. So for me, the perfect volcano is Masaya in Nicaragua. And the reason for that is it's accessible. It's got a very good road that goes up to it. Masaya is pretty much everything that you can see in this picture. It goes right over to the far horizon, and you can see a huge lake in the middle distance there. That's part of the enormous caldera that makes up Masaya. So here's a bird's eye view. You can see the town of Masaya over there on the right, home to about 100,000 people. The Masaya Lake, which you saw in the last picture. And the dotted line marks out the extent of the Masaya volcano itself, or the volcanic area. And all of the activity historically has been within the summit area. There's slightly raised ground and some active craters at the top there. And this is what it looks like. Little wispy clouds coming out of it much of the time. It's actually, we call it persistently degassing, and that's just what it says on the tin. It keeps degassing. Gas keeps coming out of the volcano, and it's mostly water. A lot of carbon dioxide, sulfur dioxide, and other gases too. But it has cycles. There are periods of time when it seems to be doing this rather more than some other times. Under quieter circumstances, when there's not so much degassing going on, the local environment looks something like this. Lots of crops are grown, and there's lots of tree and scrub. During a period of intense degassing, a lot of the vegetation just dies off. Looking down into the crater bottom, when you're right at the top of the volcano, it looks slightly different every time that you go there. On this particular time, there's a hole at the bottom there. The hole would be many tens of meters across, and you can see some gas coming out. Sometimes a little bit more than gas comes out of the hole. This is a small ash eruption. And other times, when there's not so much gas and you can actually see what's going on, you can see the red hot magma just below the surface there. And the black stuff that's been thrown out there is cooled magma. It's been thrown out, spurted out, and it's dried as tiny little fragments of scoria or ash. So the crater bottom changes its morphology quite a lot through time. Sometimes there's one hole that's active, sometimes there are several. And most recently, it's been very, very spectacular with this really actively bubbling and broiling away magma lake. So to make our measurements, we need to carry various bits of geophysical equipment up to the crater area and make our measurements. And here we're making gravity measurements right on the rim of the active crater itself. Now, one of the other great things about this volcano is not only its relative accessibility, but the fact the climate is quite good. It's relatively flat, apart from when you're climbing into the crater and out of the crater. And so it's a fantastic place to teach students and to have Earthwatch volunteers help us to make the measurements. So many hands make light work. The other interesting thing about this volcano is that, of course, in order to make our geophysical measurements, we have to be able to locate points all over the volcano that we come back to time and time again. Sometimes we need to come back every day, every week, or whatever, but certainly year after year after year, we need to make measurements at the same place in order to see what sort of changes have occurred. And we mark our stations or our points that we make these measurements with pins and spray paint and so on. But the local vultures also help us mark the stations, and we actually called this point Zopolotti, which is what they call the vultures there. And you can see that they've marked it very clearly for us. Something else that you find on this volcano that looks very, very barren when you're actually in the crater area. We're on a piece of lava here, right by a place where we make our measurements. And somebody here threw a banana skin away. And before I could remonstrate with them for doing that, because you really shouldn't do that out in the environment there, look who came out to have a look and to eat it. So there is life in the cracks, even in these rocks here, in where you would think was the middle of nowhere with lots of noxious volcanic gases. Perhaps even more surprising is that warm fluids seep up through the cracks in the rocks. Again, mostly water, but also sulfurous minerals. And we see lots of bees congregating in the area. These are all bees that are attracted to the moisture there. We've also found an area where solitary bees are nesting in the volcanic ash. So, what is it that's special about Messiah? Well, it's very accessible, apart from the odd lava flow, and it's just active enough to have changes so that we can actually make measurements and understand what's going on deep down in the plumbing system. And so that's it for me. Messiah volcano in Nicaragua is probably the perfect volcano.
A perfect planet.
My name is Stephen Lewis, Professor of Atmospheric Physics in the School of Physical Sciences at the Open University. My research centres on understanding planetary atmospheres. In this talk, I'd like to discuss briefly the role played by sunlight and by our atmosphere and oceans in making the Earth a perfect planet. Earth today is a vibrant blue planet, the only known home to life. Our environment is a complex, evolving system.
The Earth's atmosphere, seen from the International Space Station with the Space Shuttle about to dock. The perspective is a little misleading. The Space Shuttle is over 300 kilometres above the Earth's surface. The atmosphere is seen at the limb of the planet behind. About 90% of the Earth's atmosphere lies in the reddish region with visible clouds, which is within about 10 kilometres of the surface. Above this, the white region is the stratosphere, and the blue fading to black is the mesosphere. These layers all lie within 80 kilometres of the surface. On this image, I have superimposed a typical temperature profile. The cloud layers and all life are confined within the troposphere, where the temperature falls with height. Above the tropopause, the temperature begins to rise again, thanks to ozone heating in the stratosphere. One issue as a scientist approaching the Earth's atmosphere is that we cannot perform controlled experiments. We can use theoretical and numerical models and even laboratory analogues to test our ideas. But the Earth has two close neighbours with different atmospheres. These planets have suffered contrasting fates. Venus on the left is hot and toxic. Mars on the right is frozen and dry. Could understanding these other planets teach us about our own as well? A key factor for life seems to be the presence of open bodies of liquid water at the surface of a planet. The Earth is unique in the solar system in this respect. Other bodies have solid water in the form of ice or water vapour, and some even have liquid water trapped under an ice crust. But Earth has accessible liquid water which life can use as a solvent for various biological processes. The presence of this liquid water is due to our temperature and pressure, but it is not quite as simple as how far we are from the Sun. It is now possible to monitor the energy budget of a planet very accurately and to balance the total energy. Input in the form of sunlight, some of which is backscattered straight out to space from clouds and ice, has to balance the exact amount of infrared radiation that the Earth emits at longer wavelengths. The three planets, Venus, Earth and Mars, each orbit at a distance from the Sun, as shown here. This means that on average, over day and night, Venus receives about twice as much solar irradiation per square metre as does the Earth, and Mars receives about half as much. Using these numbers, we can calculate what we'd expect the equilibrium temperature of each planet to be. You may notice that the Earth is predicted to be a chilly -18 degrees Celsius, and Venus, surprisingly, is even colder at -40 degrees Celsius. This is because Venus has thick clouds which scatter back a lot of sunlight out into space, so less reaches the surface. Venus, as you may know, is a very bright object in the sky. Here in the lowest line are the actual average surface temperatures for each planet. Earth is a habitable 15 degrees Celsius above freezing. So, is there something wrong with the energy budget calculation in the line above? Actually, no, it's correct, but for a part of the atmosphere above the surface that radiates directly to space. The 33 degrees of warming we have at the surface on Earth is a natural greenhouse effect that has enabled life to flourish. But the Earth's greenhouse is modest compared to Venus. There, a runaway greenhouse has resulted in 500 degrees of warming at the surface, and temperatures now are hot enough to melt lead. It is the natural greenhouse warming effect and the poleward heat transport of the Earth's atmosphere that makes complex life, such as this Arctic wolf, possible even at high latitudes on Earth. And at low latitudes, open water and warm seas bring nutrients to supply an array of creatures. Even in the driest regions of Earth, like the Gobi Desert, winds in the atmosphere bring some snow, which can sustain even large animals, like the Bactrian camel. At global scales, the different weather patterns sustain life. You can see in this image that lush rainforests form near the equator, where rainfall is high. Deserts lie outside the tropics, where the warm, dry air now descends. And familiar weather systems circle both polar regions, supplying water to northwestern Europe, for example. So what about the other planets? Mars is a cold desert world with a thin atmosphere that can be seen here, with suspended layers of dust around the limb of the planet. But Mars too has weather. This image shows ice clouds and a winter jet stream, remarkably like our own, simulated on the Open University Mars Global Circulation Model. And just like the Gobi Desert, winds can bring water ice to dry regions, although the amounts on Mars are much smaller than they are on Earth. There is in fact too plenty of evidence across the ancient surface of Mars that it was once a warmer, wetter planet. These dried up riverbeds are around 4 billion years old and show that rain or snowfall must have occurred in a thicker, early atmosphere. In contrast, if Venus ever had liquid water, it long ago evaporated in a runaway greenhouse effect and is now sitting in the form of thick clouds about 60 kilometers above the red-hot surface. This image was taken over the South Pole by the Venus Express spacecraft. The night side of the planet is shown at infrared wavelengths. The bright regions are where clouds are thinner and heat is escaping from the hotter atmosphere below. In each case, the changing atmosphere has had a profound impact on the evolution of the climate of each planet. Such complex interactions form the perfect planet that we inhabit. To find out more about a perfect planet and our free learning materials, please visit the Open University website.
Thank you very much, Hazel and Stephen, for sharing your thinking about the perfection on Earth, with Hazel talking about what makes the perfect volcano to study, and Stephen talking about how sunlight, the atmosphere, and oceans have created the conditions in which life has evolved, and incredible life forms at that. I'm Dr. Julia Cook, and I'm a plant ecologist. I'm also a media fellow, and in that role, I identify the best academics to work on different series and facilitate their relationships with the BBC production teams. I really enjoy the insight that gives me into a behind-the-scenes look of a huge range of different science and documentary productions, both in my field and lots of others as well. Perfect Planet has been an extraordinary series with many stunningly shot sequences and fantastic scientific narration that's captured the attention of millions of viewers, both interested and concerned about the Earth. I'm now going to ask Stephen and Hazel your questions about their research and involvement in the series and in our free poster that you can order. So please type in your questions into the chat box. But just to start off, I've got a question for Stephen and then one for Hazel. So Stephen, I think you've been involved in a couple of series, but I wondered, as an academic advisor, what has been your role in Perfect Planet?
So I was involved in Perfect Planet for up to about 5 years before you actually saw it on the screens. It's a long process. We start off with a proposal, essentially from a production company. As you may know, the Open University doesn't broadcast overnight anymore with our sort of lectures direct, but a lot of our content does go out in the form of these high-profile series, and probably the highest profile of all are the David Attenborough landmark series, of which Perfect Planet is the latest. So I would have got the scripts, the proposals. I talked to the production company in the early stages about how to organise the programmes, and we decided to theme them around really what they like to call the forces of nature, the idea of volcanoes, sunlight, weather, oceans, and now man being, or humankind, I should say, being the forces that are controlling what's happening on our planet. So we took the film that we had and we worked it around those themes rather than, say, filming a particular species or filming a particular area of the world. I would then get the scripts and comment on them. So long before Sir David ever saw them, we would have had scripts from the production company and sent by me, and then I would make my comments on them and say, well, I don't think that's very clear, or actually, no, you've got the number wrong there, or something. And they would maybe take them into account, maybe not. They're sort of sent backwards and forwards several times. And then I see a lot of the footage. So I've seen a lot of edits to the program. I have to say, it's I think that one of the testaments of how good the program has been is that I haven't got bored with it, because for every minute you see on screen, I think the number that we were given is there were 200 minutes filmed. And I've seen a lot of those in the edits, not all of them by any means, but they've been edited down. But I've seen a lot of things, a lot more than people have seen on the screen. And hopefully we selected the best bits, if you like. But it's because of that very high ratio of filming to the amount you actually see that the quality of these programs is so high.
Amazing, and an extraordinary sort of collaboration between storytelling and how to tell a story that's going to keep people entertained for so long, as you've said, and then making sure all those details are spot on accurate. Thank you. And Hazel, I really enjoy it when I go to schools or other people's workplaces and I see these posters, such as you can see behind Stephen now, and we've produced one for Perfect Planet. How do you decide what goes on a poster, and what did you think just had to be on this poster about volcanoes? Well, volcanoes are, as we know, a very important part of this series. So they kept popping up. It wasn't just in the first episode, which is really, really good, because I do think that volcanoes are probably the most important thing to study. So I was really pleased to see that volcanoes made it to the front and the back of the poster. And it's always a little bit of a trade-off between the different messages that you're trying to give. So the poster is there to attract the eye and to be a reminder of this wonderful series. It's a sort of multimedia presentation, isn't it? It's a paper presentation of something to remind people to go and see the digital version of it. And we had... in the end, a very small amount of real estate on the back of the poster for each of the episodes. And so for me, it was about identifying just a few key facts and figures that really the sort of take-home messages about the volcanoes that came out of this series. And I think the way that the poster worked very well was that we had that same format for each of the different episodes, and so that's what makes up the back of the poster. But I do hope that people order 2 posters so that they can display both sides at the same time. That's always a challenge. All right, we've got some great questions coming in. So a question for you, Stephen, and I hope I'm going to pronounce all the parts of this question right. But the question is, do you think there was ever an ocean in Valles Marineris? Is that how to say it?
That's Mariner Valley. You can say if you want to stick to English. That
okay.
will be that's fine.
Thank you.
So Mariner Valley. Let's say that it's an enormous rift, kind of rift valley near the equator on Mars. The Grand Canyon would be a mere tributary to a tiny bit of it. Now, I don't think that was never an ocean. It's clearly resulted from volcanic activity. Actually, there are huge volcanoes on Mars, much bigger than the ones on Earth. There's Olympus Mons is 3 times the height of Mount Everest, and it's literally has the footprint of France. If you want to get an idea of scale, one mountain has the footprint of France, so it's huge. But the whole of the Thosis Ridge, which is where Valles Marineris is located, is a big volcanic outcropping. So that was all being pushed up and split apart, and it's probably a bit more recent than the ocean on Mars. Now, we think there probably was an ocean on Mars around between 4.3 and 4 billion years ago. Now, the reason why you'd expect that is simply because you'd expect Mars to be made of a similar mixture of things as the Earth was, and you can sort of work out how much water there should be. And there's a region of Mars all over the northern hemisphere, the boreal plains, which is remarkably flat and young-looking and smooth compared to the older southern highlands. Now, that's maybe a clue. And you can basically take a topography model of Mars and fill it up with water by computer, the amount of water you think was there, and indeed you would see an ocean sitting around the North Pole of Mars, and probably coming up to a shoreline somewhere very close to where, the Mars rover is often landing. In fact, Perseverance will be landing tomorrow night, somewhere close to where the edge of that ocean might have been the ancient shoreline, but we're not entirely sure. Of course, this disappeared maybe 4 billion years ago, and then Valles Marineris and various other features were created and changed more recently in the period called the Hesperian, when ice under the surface melted and collapsed. So these are more like the sort of features you can see in North America, actually, where you get mega floods, ice below the surface melts periodically and the surface collapses. And those are the kind of geological features you can see around Valles Marineris, and you can see outflows to the northern lowlands where we think there might once have been an ocean.
Extraordinary, and I guess people are eagerly waiting to see what happens with Perseverance to add even more information to what we already know. Right. Yeah. It will be. It'll be a fantastic new mission. It's great to go somewhere new on Mars. I mean, we've landed there a few times, but not that many. If it just had a few pinpricks on Earth like we've had on Mars, then maybe we wouldn't really understand the Earth very well at all. So just a few points we've landed at, and Perseverance will be a great mission, I think. Brilliant. So that conversation started at oceans and went to volcanoes. So we'll continue along volcanoes, and there've been some excellent volcanic jokes in the chat box as well. So a question from Rory to Hazel is: have you had any close calls or tight situations when you've been working close to volcanoes? And related to that, are they unpredictable, or do you know when they're going to erupt, and if so, how?
Wow, there's a lot in there. Okay, so some close calls. Well, I don't know whether I should say too many of them, because I try to forget them immediately afterwards. But I did have an occasion when it didn't even seem to be in a volcano, because I was actually in a forested area at the bottom of a volcano, but my foot sort of fell through the ground. Like sometimes happens, the ground just gave away, only my foot ended up in boiling mud, which was seriously scary. And so that was a close call, in that only my leg fell in. That involved a week in hospital in Costa Rica, which has a wonderful health system, I have to say, but it's definitely not something I would like to experience again. And another time I was walking, I had to get back to the other side of the lava flow. And so I thought, well, I'll just run across it. Now you don't run across an actively moving bright lava flow, obviously, but the top of the lava does cool relatively rapidly, and it's very dark. And if it's a slow moving lava flow, it's not entirely obvious that which parts are still active and which aren't. So you can tell afterwards, because the bottom of your boots have melted. So, can we predict volcanic eruptions? Well, the closer we get to an eruption, the better we get at it. It's a bit like the weather from that point of view, isn't it? But volcanoes usually give some sign that they are moving into a period of unrest, it's called. So they sometimes inflate a little bit before erupting. They give out a lot more gas, perhaps, that sort of thing. But rather confusingly, sometimes they stop doing that sort of thing. So if, for example, you were looking at a volcano that always has a lot of gas coming out of it, if it has a period of time when there's no gas coming out of it, that could mean that the vent, or the hole where all the gases are coming out, has become blocked in some way by a landslide or something. And that often means it's going to have something of a hiccup. Now, the hiccup can be just a very gentle type thing, or it can turn into quite a large explosion, which could well, potentially have global impact, but certainly locally, environmentally. But actually, the really interesting thing is that whilst it's quite hard to predict when a volcano is actually going to erupt, it's even harder to say when it's going to stop erupting. And often that's really, really important for the people who, particularly those who are living nearby a volcano. They need to know when they can get back to plant their crops, when they can open the schools again, and all that sort of thing. So it's not only when eruptions are going to start, it's how long is this eruption going to last for. It's a bit like being locked down in a pandemic, isn't it? It'd be a lot handier if you knew, well, Tuesday week, it'll all be over, don't worry. It's not that easy in a pandemic, and it's not that easy in a volcanic eruption either, sadly.
Can I add on a little question to that answer? So when you're detecting volcanic movement and responses, do you use sort of Earth observation, so sort of satellite imagery, or do you have sort of things on the ground that are measuring which way do you look for changes in the Earth's surface?
Bit of both, and increasingly it's done from space, because it's a lot easier to cover a huge amount of ground, of course. And most volcanoes are not monitored at all, and it's extraordinary, but it's the case. Most volcanoes are not monitored at all. Then several are monitored through space, but most of the satellites that we use don't look at the volcanoes all of the time, so they're coming back every several days, and in some cases once a month or so, over the volcano and looking down and looking at it. So there are very few volcanoes that have permanent installations of seismometers looking at small earthquakes, that sort of thing. But they're actually in the minority, which is really surprising. People would assume that we've got it covered. We've got all these volcanoes being monitored, and I'm afraid we really don't. So
a very active area of research onto active volcanoes. Right, Stephen, some questions have come in for you. Rachel asked, what might have caused the cooling of Mars and led to the loss of water there?
Right, that's an easy one. No, it's not at all easy. We have no idea. It's a very difficult problem. I mean, you remember, we're looking back way back into the past. So we're talking long before. I mean, there's really possibly a few, or possibly almost no evidence of anything that old on the surface of the Earth, because it's all been churned up and subducted, and various processes have happened. So we're looking back very early in the solar system. What we think probably happened, although it's very unclear which way round events happened, is that the magnetic field at some point on Mars turned off, or at least it certainly had one in the past. We can actually see a fossil magnetic field in the rocks on the surface, which we can see even from orbit. But it's not an organised magnetic field like the Earth anymore. It's just fragments left in the rocks. Now, why did that turn off? Well, the simple sort of explanation is often that the core of the planet cooled down because the planet's smaller, but it is smaller than the Earth. It's about half the size of the Earth, half the radius of the Earth, but it's not that much smaller than the Earth that it would have cooled off and solidified that quickly. So this is a bit of a puzzle. Some people believe that some catastrophic event might have happened, for example, an enormous asteroid. Something happened that disrupted the magnetic dynamo anyway. And it probably is. It is also true that the planet's cooled off more. The crust is much thicker than on the Earth. Anyway, the magnetic field turns off. That removes some of the protection from the atmosphere. We think also the fact that we knew there was precipitation on Mars. I just showed you a few river valleys. There's loads of rivers all over the surface of Mars on the old parts. We think there was rainfall or possibly snowfall. To have that, you must have had a much thicker atmosphere than we've got today. You can't have liquid water on Mars. You might be familiar with the fact that if you go up Mount Everest, water boils at a lower temperature. Now, water always pretty much freezes at 0 degrees Celsius, but it boils at 100 degrees at sea level, but that number drops as the pressure drops. Now, what's happened if you go up to, say, we don't really notice on Earth because we're mostly pretty close to sea level. Most people live pretty close to sea level, within a few hundred meters. But if you go up our tallest mountain, it drops to about 80 degrees. Now, imagine going up and up and up. And actually what happens eventually is that the boiling point reaches the freezing point, and that's known as the triple point. And actually Mars rather curiously sits right at the triple point of water. So probably what happened is that the pressure on Mars fell as the atmosphere was stripped away by the solar wind. And then as the pressure fell, there was a smaller and smaller range over which you could have liquid water. And eventually the water, you got to the situation you've got today where the water is either frozen solid or is in a vapor in the atmosphere, but it's not lying around in pools on the surface. If there is any liquid water on Mars now, it must be in some sort of sealed unit underground, maybe an underground lake or something that's sealed by ice. And this is what I was talking about earlier with the mega floods on Mars, that probably as the pressure in the atmosphere dropped, then the water from the ocean sank into the surface, froze into these ice blocks. And then there's still geothermal activity going on. We know there have been volcanic eruptions much more recently than that on Mars. In fact, probably we don't even know that Olympus Mons is inactive now. It might still be erupting. It might have erupted in the past sort of 2 or 3 million years, which is a long time to us, but not very long to an Earth scientist. So the geothermal activity might have melted that ice, and that's what's caused the mega floods that we see in the period from about 4 billion to about 3.5 billion years ago. So it's a long, complicated answer, but it's actually another good example of one of these complicated coupled systems. So the water, if you like, the liquid water keeps everything lubricated and keeps things moving around on the surface, and that allows an active cycle. And as soon as the atmospheric cycle shuts down, you start to lose atmosphere, then everything goes wrong, if you like. The water freezes, the pressure drops, and you get this sort of dry, low pressure desert you've got today.
Incredible. And there's a question that sort of follows on from that. So if we're not quite sure how the cooling happened, do we know how long the cooling took?
No, is the simple answer to that. I mean, we know quite a lot about ancient Mars. Well, I say quite a lot. We know a little about ancient Mars, and we know quite a lot about what Mars is like now. And we think Mars it changes a lot on timescales. There's all sorts of evidence of climate change on Mars. You can see layers of different coloured ice and so on. But it's been in a climate relatively like it has now for the past 3 billion years, which is what's called the Amazonian period. And that's characterized by relatively low pressure and which might vary, and by typically no, not very much liquid water, solid water. Maybe there's certainly been snowfall on Mars because you can see glaciers. There's still glaciers there. And so we kind of know what it's like now and for the past 3 billion years, and we kind of know there was liquid water in a high pressure atmosphere between about 4.5 and 4 billion years ago. But how you got from 4 billion years to 3 billion years ago is very fuzzy. And there's a kind of dashed line which we just have to draw between the two. So yeah, that's a really active area of research, and there's lots of people all over the world thinking and working on that, but it's very difficult. There's very little physical evidence, and the modelling is very complicated. You're trying to model something you've never seen. It's very hard. And
when you can't just duck out for the weekend and go and collect some more samples, just stuck over to Mars. Not unless you've got a few $1 billion to spare, and it would take you several years as well. Yeah, and maybe we will get a sample. We're starting to think about getting a sample back from Mars right now, but it's going to take a decade and a huge amount of work from lots of space agencies combined. So it's a vast undertaking just to get a small test tube of Martian dirt. So it's not easy. Incredible. Thank you. Now we're going to switch a little bit and come to a question much closer to home. Hazel, what's the relationship between volcanoes and geysers?
Well, a geyser or geyser, depending on where you
Australian.
Exactly. Yeah. Tomato. So geysers are spurts of superheated steam that project the groundwater up. And so Old Faithful in Yellowstone is probably the most famous of those. So the ground looks nice and quiet and relatively flat. And if you watch it for long enough, you'll see gradually an enormous bubble comes up underneath and brings the water up with it. Huge bubble that explodes, bursts, and this jet of hot water goes all over the place, and it is just groundwater. So that happens because you've got groundwater, and the groundwater is heated because in the case of Yellowstone, you've got a rather large body of hot magma at relatively shallow depth heating it. So another place where you get a lot of these things, and some famous ones in Iceland. And again, it's because you've got relatively shallow hot magma heating the groundwater. Very spectacular things. Although one of them is called Old Faithful, and it's called Old Faithful because it was very faithful and would carry on erupting almost on demand. Sometimes they don't continue forever, because what they need is, of course, the heat source, and that's pretty much going to stay there throughout our lifetimes anyway. But the water levels can change due to human habitation as much as anything, so if there's less water, then you don't see that spectacular thing happening anymore.
Thank you. So you mentioned that the heat source sort of stays, or is sort of more stable possibly than the water source. Rachel has asked, how do you measure the extent of a volcano, or how wide and how deep that sort of magma extends?
Oh, that's a really good question, and it's a bit like some of these ones. It sounds like, well, of course there ought to be a way to do this, and it's a bit like, actually, if you say how many volcanoes are there, or what's the biggest volcano, those sorts of things. It's not that easy, because it sort of depends how you count it. Now, the top of a volcano is relatively straightforward, and you can figure out what the number is there, what the height is. But where is the bottom of the volcano? Is it the local town at the bottom? Is it where the slope suddenly changes to flat? Is that the bottom of the volcano? Well, maybe not. And not all volcanoes actually are pointy peaks with snow at the top of them. In fact, most of them aren't. So it's not as easy as all that to even say how far out it goes. It's certainly, you can't just say, well, where do you have volcanic rocks? Because the lava flows can travel huge distances away from the original vent. And so we can use geophysical methods. We use gravity and magnetic measurements in particular. Some other electromagnetic techniques to probe inside the volcano. And so we can look there for contrasts in density or other physical properties. And when we see contrasts, we can say that there are differences, there are different bodies down there. And so just as you use these sorts of techniques to probe for where oil and gas reservoirs are, you can do the same thing for magma reservoirs. And so you can look then to see how deep down a large body of magma is. The further away it is, the more difficult it is to spot it, of course, but you can probe quite well to several kilometers down below a volcano and see the size of these bodies. And they are absolutely enormous in many cases, tens of kilometers easily across. So absolutely humongous.
Incredible. Yes, I guess I sort of think of them as kilometers across, but not tens of kilometers across. Right, so looking at behind you, Stephen, somebody spotted that there's a planets poster as well as a perfect planet. Did you work on the planets as well?
Yeah, I had the same role on the planets. So I've done this twice recently, and it's a fantastic part of the job, I have to say. It's there's a lot of things you do as an OU academic which are very similar to other academics in other universities. We have PhD students, we produce courses or modules, we do all that kind of thing. But actually working with a TV production company is something that we do that most other academics don't get a chance to do. We maybe get interviewed once or twice for various specialist things, but to actually sort of sit almost embedded with a production crew for the length of a production is great. And the planets was a really good experience as well. It was different from Perfect Planet, obviously. It was slightly different people, but very similar roles. So I was in at the early stages talking about how we would do the series. They knew about 10 years in advance they wanted to do a planet series, and that's the kind of wind-up timescale. I mean, I wasn't involved for that long. I was involved for about 4 or 5 years again. And then I worked. There was a different script writer for each episode actually, and they would produce a sort of outline script, and then I would get sent it, and there would be various phone calls and debates over various things they wanted to say or how to say things better or more clearly. And then I talked to Brian Cox when he was actually doing the presenting. So in that case, I had a few phone calls and we discussed how to explain a few things. And then it's a huge collaborative effort. There's a lot of different people involved, and it's really interesting to see how these things go.
One of the things I really enjoy about my job too at the moment is going from that first production meeting where you hear a producer's vision for the series and they're explaining what they want it to look like, and then yes, 4 or 5 years later, when you watch it on television, you know how many twists and turns and challenges have come along the way, and you see this series and their vision has been realised, and our role in helping them realise that vision with the accuracy, with the kind of latest information is very rewarding. I think also our teaching experience comes in as well. You were talking about different ways to say things and finding ways to explain really complex things as clearly and in sort of everyday language as possible. I think our teaching comes in there.
Absolutely. So it's very important, of course, in these series, we have to explain. We don't want to say something that's wrong ever. We've got to say things that are true as far as we possibly can. But at the same time, we've got to make it accessible to everybody, and this is a big challenge. You know, we're not kind of lecturing to a highly selective group of people who've all done A levels in various subjects and then all done various courses beforehand. We're talking to everyone, and we've got to try and make it sort of engaging and interesting, and simplify it in a way, but simplify it without making things wrong or oversimplifying. And that's a real art. I mean, I think I really it's a hard thing to do. It's very easy to get, especially if you work in an area of science, to go off into a tiny sort of specialist area and write papers that are inaccessible to most people. Certainly, many of my colleagues write papers I have trouble reading, and I'm sure vice versa. But writing for everybody to understand is really important, because after all, that's why we do this. We're supported by public funds, and we want the public to be interested and involved in what we do, I think.
I agree completely, and it's a great challenge, to communicate things clearly. All right, there's lots more questions, so I better get back to these. Where are we? I'll go just to the last one because it's just popped up. Do volcanoes ever die completely? And if they do, why?
Okay, so yes, volcanoes do die and become extinct. We have some in the UK, and our last volcano is Lundy Island, in fact, just off the, we're just in the Bristol Channel. So that's dead, gone, buried. It will not erupt again. And the reason that we know it won't is because the tectonic setting is such that it can't erupt again. So volcanoes erupt usually at the edges of tectonic plates. So we've got a huge long line of active volcanoes down the middle of the Atlantic, for example. So that's where the plates are pulling apart, and you have volcanoes popping up underneath the ocean all along there. And of course, they hit the surface at Iceland, where you've also got a hotspot in that particular area. Other places where volcanoes occur is where plates are crashing into each other. And we see that all around the Pacific Ring of Fire. Those are all volcanoes, and they're all caused by the same thing, plates colliding into each other. Now, in the UK, way back, there have been several different periods where we've had active volcanoes. The UK is a very complicated geological amalgamation of the Earth's history. And so the most recent volcanoes were active 60 plus million years ago, when the tectonic situation was such that there was some break apart plates. That's not happening anymore. We're on a solid bit of tectonic plate now, so those volcanoes are not going to erupt again. Interestingly, we don't talk about volcanoes being extinct we give them quite a long time to not erupt. And it was interesting that Stephen was just talking about Olympus Mons on Mars, and that's certainly not done anything for many millions of years. But It still could possibly, because everything happens rather more slowly on Mars. Now, on Earth, if a volcano has not erupted for 10,000 years, then we might begin to say that it wasn't active. But technically, a volcano is active if it's done anything within the last 10,000 years.
Amazing. That sounds like being quite careful, because I guess the risks associated with underestimating a volcano are big.
Right.
Oh, I'm torn between two questions here, but you mentioned Olympus Mons, so I'll go to that question next. Stephen, if Olympus Mons explodes, what would that look like? And would it literally be lava that came from it, or something else?
Yes, Olympus Mons is a shield volcano, as Hazel would recognise on Earth, except it's just bigger, much bigger. In fact, one of the things to say is it's so big that it would actually be a very boring mountain to climb. If you were a mountain climber, it would just be an extremely long walk. Really, it wouldn't be a climb. But we know it's erupted many times in the past, because you can see evidence of different eruptions in the caldera, and there's also seepage from various vents and things on the sides. So it's still been geothermally active quite recently. Maybe extinct by Hazel's terms, but it could well happen. And indeed, it throws out ash and lava. There's basaltic rocks all over the surface. And in fact, you can see the ash from the volcano. It's clearly been blown very high into the air, and gravity on Mars is about a third of that on Earth, slightly more. But it's so things will go high when they're blown out with great force, which they are. And you can see evidence of lava flows all over the surface. You can see lava tubes, all sorts of evidence that lava has flowed and solidified and weathered. And you can see remnants of ash all over the plains to the west of Olympus Mons. And there are many other volcanoes on Mars. There's Elysium and the three down the Thosis Ridge. And similarly, you can see evidence of their output all over the surface. So just like on Earth, you may remember when the volcano in Iceland that I won't attempt to pronounce. I'm sure Hazel will do it much better than me. But I have been there, and I've also experienced disruption from the ash that came out of that. But that's a baby compared to these ones. And you can see, but volcanic ash, aside from the gases that come out, the volcanic ash has a huge impact on Earth's climate. So it's not just disrupting air travel. Certainly, I think in recorded history, there have been famines as a result of crop failures from changes, and it's still to this day. You can see the huge impact of Mount Pinatubo erupting, which is monitored by satellites just around the time we were building a lot of Earth observation satellites in the 80s and 90s, and that was seen in the 90s. So volcanoes have a huge impact on climate. In fact, probably volcanoes got us out of a frozen state in the past. So it's the ash and dirt, if you like, from volcanoes that would have discoloured the snow when Earth has been in various frozen climate periods, and that would have made it absorb more sunlight and warmed us up. So we've got them to both thank as well as fear.
Well, that leads beautifully into another question that's come through. So somebody's written, how much pollution would a volcano create when it erupts? And I guess if a volcano on Mars erupting, we might not call it pollution in the same way that we might on Earth. Hazel?
Well, the thing is, you can have a very quiet volcano that's just doing its thing all the time, like the pictures I was showing of Messiah volcano. That's erupting all of the time. Locally, it's quite important. And I showed some pictures of crop destruction, for example. And in fact, some of the local people have asthma, and there are some skin conditions that may be caused by the gases and some of the ashes that are coming out. But that's relatively local. But as Stephen was saying, there have been many volcanic eruptions in the past on Earth, which have had quite significant impacts. Now, since Stephen mentioned Pinatubo, it erupted in 1991 in the Philippines. That was a fairly large eruption. It was rather interesting because it was one of the best monitored ones. We began to have good satellite data on that, and we could see the sulfur dioxide cloud and the ash going right around the globe. We could actually see it in the satellite images. So it was just really very, very interesting. So it depends where the eruption is. If they're relatively close to the equator, the ashes and gases and so on can spread either side of the equator. And of course, that's where most of life is on the Earth at the moment. If you have a polar eruption, its impact can be rather less, because just the way the global circulation works, the ash and so on would stay relatively local. Not all of it, but it would stay relatively local. So I guess it depends on where the eruption is and how large it is, and how long it goes on for. So a very quick explosion, for example, that lasts a day or two, will have relatively limited impact. It'll throw up whatever it's going to throw up, and then it will take a number of days or weeks for the materials to fall out of the sky, basically. But some eruptions go on for weeks, months, years, even decades. And if they are quite extensive eruptions at the same time, those are the ones that cause global climate change. And there have been half a dozen of those in the past, which have caused mass extinctions.
Thank you. Well, our time is sort of running out, so I've got one more question in the chat box, and then I thought I might sneak in a couple more questions from me. So Chris and Ruben has asked, where would you find live eruptions today that would be like the fissures that spewed basalt all over Northern Ireland?
Okay, well, Kilauea in Hawaii is probably the easiest place to go to. Well, not right now, but under normal circumstances, is a good place to go to, where you can see basaltic rock being poured out, and it forms these pillow lavas and so on, as the sort of thing that you can see in Northern Ireland. Here's a bit of basaltic rock. This is the sort of thing that would come out of that kind of lava flow. So yeah, Kilauea in Hawaii would be probably the best place to go to see that right now, or any of the Icelandic volcanoes when they're erupting.
Brilliant, thank you. So our hour is nearly up, but I wanted to go back to Perfect Planet and ask both of you what your favourite sequence was in the series and why. Stephen, I'll start with you.
Okay, that is a tough one. I mean, I'm tempted to mention a few actually. One of the things I really enjoyed, I think, were the Bactrian camels in the Gobi Desert. So they're amazing beasts. I've seen Bactrian camels in real life, and I've been to deserts, but I've never been to the Gobi Desert. So even if I had, I think it's very unlikely I'd have seen them, because there's so few of them left. And the film crew did a heroic job. I think there was a segment in the making of bit that we get tacked onto the end in the last 10 minutes of that particular episode, of the weather episode, where they showed them trying to chase and find these camels. And yet they're enormous beasts. They're really, really big, impressive beasts, and yet they can survive without a drink in the winter. They have to eat snow, which is really, it's a really tough environment. You can see the plants are all dried up and bush-like. I mean, you might imagine small creatures or insects could live there, or maybe even very, very small forms of life, but such a big, impressive form of life. And I'm going to cheat and have another one, which was actually a small sequence with the eider ducks, which I really enjoyed, because they're big, strong ducks, and they're swimming in a tidal pool in it's somewhere near Scandinavia, and it was just so beautiful, the patterns of perhaps I'm a fluid nut working in atmospheres, but I really loved the swirling patterns of the tides and these amazing ducks following around the streamlines of the flow. So I really enjoyed that.
Brilliant. And Hazel?
Wow. Well, again, there are just so many excellent pieces, aren't there? But I'm going to choose one from episode 1, which was San Fernandina volcano in the Galapagos. And it was the images of those huge iguanas slithering their way down into the crater. I just thought that was so spectacular, not just because they're such great big impressive animals anyway, but that they're doing such an amazing thing, slithering down through those rocks to get to the crater bottom to incubate their eggs. But also that the cameramen had to go down there too, or camera people, should I say, had to go down there too, and carrying all the kit that they had to. It's just so impressive that they managed to get that footage. That was truly awesome.
Extraordinary. Yes, I've seen land iguanas in Galapagos when I visited my parents there some years ago, and I've seen the land iguanas, but certainly not that behaviour, which I agree, to be able to make that behaviour visible to so many people is just extraordinary. All right, so the last question for each of you is, there was a lot of wonder and awe in the sequences in Perfect Planet, but sort of some serious messages too. What would you like people to take from Perfect Planet, from watching Perfect Planet? I'll go back to you, Hazel.
That it's fragile. We have a perfect planet. It's our only planet. It's fragile, and we need to take care of it.
And Stephen?
A very similar theme. It's the complexity of all the systems on the planet. But if any one of them gets out of balance, or at least large life forms like us are in trouble. The life probably won't go extinct as a whole, but there've been plenty of occasions in the past when 90% of species have been wiped out by changes to climate and changes to the planet. And we're quite capable of doing that. I mean, the sort of statistics about how much we're emitting compared to volcanoes now. I mean, we can see the effect of volcanoes in the climate record. Well, we're a mega volcano times 100 or something. So we ought to be careful, because as well, the thinness of the atmosphere, I was trying to show in the start of my talk, we're in this tiny, all the life we know about really is within a few kilometers up and within a kilometer, a few kilometers down, and that's it. We're in a tiny, thin, fragile shell in a otherwise pretty hostile solar system and universe, so far as we know. So let's not muck around with it too much, I think.
No, thank you. Looking at all the questions and the activity in the chat box and things gives me an enormous amounts of hope. There's obviously lots of people that care and are interested and know a lot and want to learn more. So I find that very encouraging. But we are just after 8 o'clock. So to close, I wanted to say thank you so much to everyone who joined and watched this live and watched the recordings later for joining us this evening and such great questions. I hope you enjoyed the conversation tonight and enjoyed learning about this powerful and fragile perfect planet. A huge thanks to Stephen and Hazel for their time. And I'll leave you with some final words from the Northern Ireland OU Director, John Darcy. Thank you. Good night.
Good night.
Good night.
What a fantastic talk. Thank you, Hazel and Stephen, for joining us this evening and for delivering such an engaging event. If you want to keep in touch with the Open University, please do follow us on Twitter at OU Belfast and on Facebook at Open University NI. Finally, on behalf of the Open University and the Northern Ireland Science Festival, I do hope you enjoyed tonight's event, and thank you all for joining us. Take care.